All right. Good morning. While you are answering this question, I want to spend a couple of minutes to address some of the feedback I always collect it, and I'll always read it. So I want to thank everybody who gave feedback. So all people from this pile are late. Just some of these, you know, the copy is on the blackboard since no names, so you can read them. Also, the answers to the exam. And sometimes TFs contradict each other. Yeah? That's a perfect opportunity for you to become active and say to a guy, you know, that TF told differently, so who's wrong, you or that guy? Not in any particular order. Long statement about different aspects of fairness. Well, yeah, what is fair depends on many circumstances, but in every course, it means that everybody has exactly the same conditions here. Outside of this, outside of reach of anybody but you. And I agree that some of you may have longer hour at job, some don't have any job, some might have families. Well, those circumstances may be different for different people, and maybe Boston University, as any other university, should address, well, in that case, I suggest become active politically, go to student union, push your agenda for more accommodations. When people upstairs will hear you, people here on this floor will have to follow. Right now, everything is according to the current policy, and only policy makers can change the policy. So vote. Wires, etc., is hard. Yeah, we would like to have more computer simulations. Well, that would have been physics, so it's a different course. If it would be my way, you would be doing much more wiring and hand-on stuff. Well, I just read it because every time someone writes it, I wish professor would write better. Me too. Well, this is several lectures not helpful, homework not helpful, and for preparing for the exam, maybe, yeah. For some people, you know, the same actions lead to different results. That's natural. The only thing I would disagree is that majority of the class used all 2 hours for the exam. No, actually, about 20 people, which is a third left till the very end. In labs, we would need to have everything we need beforehand, like equations. No, it's not going to happen. That's what notes for. Use your notes, use your peers. use your mind, work. And again, standard, very standard, meaning labs are long. Yes, because this is how they have been designed. It's a combination of lab and discussions. And they have to run for 3 hours and 30 minutes. So anything longer than 3 hours and 30 minutes could be said long. Anything shorter than 3 hours and 30 minutes, not long. Well, and you feel free to send any feedback. You can use Piazza without any name, anonymously. I like reading it. I don't disagree with everything, but why would I? I have a particular set of skills acquired over a long career. So, let's check. That was question 2. Two and 3. Somewhat harder. Well, of course you don't know what to expect, especially if you haven't taken PY105. And more or less as, well, again, the distribution is very, very natural. I don't see any something, you know, very different from past years, which means I think we're right on track. So this is statistics, which if you would like to, you could check on Blackboard, you know, at least average. And what I see is about 50% fall in the range AA minus, and about, well, now we have, I think, 62 or 63 students, 48 within B and A. So I think it's pretty good. And I always say, if you're satisfied with your grade, just keep doing what you've been doing. Seems it works for you. Otherwise, you should rethink your strategy, you know. And what does it mean? Well, that's a copy from the first lecture slide. The exam problems, not identical to homework problems, and they have different sources. One exam problem might have different sources in it, which might come from class or lab, and just, you know, drilling the problem solving also is not sufficient on its own, because also there is specific logic behind recognizing a specific situation and applying a set of equations related to that specific situation. It's more than just drilling. It also requires recognizing, and that requires special activities, special mental activities called understanding. And understanding has many different levels, starting from words, sentences, and lots of stuff, of course, for understanding can be done here, but the practicing cannot be done here. The nature of this course, it's a standard lecture, homework, lab course, so practicing is supposed to be done outside of the lecture. Now, we are starting a new topic. So this is how much we're going to learn in 2 weeks. And we will. And the question number 1 is this. I've got nails, and I've got a rock, which, well, it does look like a rock, but actually it's something different. As you see, it lifts these nails, which means we're observing interaction, which means there is a force. And naturally, the question is, What force is that? So you should read, choose your answer. Now, it will take you maybe 30, 40 seconds. I'm going to use this time to answer one more opinion. I am perfectly aware that different students benefit differently from lectures. Some may not benefit at all because they already know everything. But again, rules are rules. We have to follow them, whether we like them or not. Of course, you can take a risk. You see the red light and you drive through, but there might be a policeman, maybe not. You may be lucky, maybe not. If you take a risk, that's on you. And the answer, of course, is that cannot be gravity, too weak. To exert a strong force of gravity, mass has to be giant, like a planet. No strings, no springs attached, so not elastic, not friction. Friction requires, well, kinetic friction at least requires motion in contact. That's not normal force. The surface is very weird. Not electric, so neither. The worst possible answer could have been all of the above because it doesn't make any sense. But of course, that's a different force, so we have to study property of that force and we have to give it a name first. And because, well, of many historical reasons, we call it a magnetic force. So all we need to have is a compass like this to see how other magnets might affect. So what do we do to study this particular force? Well, we need a test object, not a test charge. In this situation, a test magnet. And that's a standard magnetized needle. And if we walk around and we look at it and we don't see any particular arrangement, that means in this area there is nothing acting on it. But if by any reason we observe a specific arrangement when we have many, many different compasses, in that case, we say there is a magnetic force acting on each compass. And now we also say there is a magnetic field in the area. Yeah, sure. Of course, we could just use one and move it around and see what's happening to it. But we can just use many, many compasses. We can see they are affected. That depends on the location. And in the past, to see an electric field, we use grass seeds in oil. Now we can use the same idea, not grass seed. Yeah. Dielectric is not affected. Well, doesn't feel a strong force for a magnetic field. But if we have iron filings and a magnet, we can see the magnetic field. All we have to have is eyes. Here. Those are magnetic field lines. Each iron filing is acting like a tiny magnet. Well, it's actually much more beautiful if you could just look at it, actually. You can just look at it. Yeah, and you can pass it around. Yeah, don't be stingy. So, next step, of course, is given a definition of, well, if it's a force, it's a vector. as every vector, it must have magnitude, certain direction. So the next step is to give a definition of how to calculate that magnitude and how to calculate and how to define or state the direction. And this is a definition of a direction. We start from it. If we have a compass, a magnetic needle, if we place it and it has a specific orientation, for each magnet, first we name the ends of the magnet. We call them poles, and one we call north, second we call south. And for each magnet, we know that two magnets, when they face like poles, they repel each other. See, repulsion. But if they face opposite poles, south and north, in that case, they attract each other. And that's why a needle always has a specific orientation if we bring it close to a magnet. And according to a historical definition, at the location of this compass, the direction of the magnetic field is taken from south to north as viewed inside the needle. So magnetic field lines are lines, and different sources, not just a magnet, generate magnetic field. And if I take a wire and I too strong, move away. Does it work? Okay, yes. So if I take a magnet, a compass, and I place it close to a wire, I just know that one single wire doesn't generate very strong magnetic field, so I need several wires together. And I can see that as soon as I connect a battery, there's electric current, and electric current starts affecting this needle, which means a wire with electric current also acting like a magnet. We will talk about the strength of that magnetic field later. For now, it's just a combination of facts. Not just a magnet generates magnetic field. A wire with electric current is acting like a magnet. So if I have a compass and I place it close to a wire, I will see that it is affected. And now, according to a definition, if I look at the compass and I know, well, again, normally the red pole represents the north pole of the magnet and the blue pole represents the south. And if I let it stabilized, so inside of the magnet, the direction from south to north will represent the direction of magnetic field at the location of the magnet. But outside, magnetic field doesn't stop at the end of the magnet. It goes outside and go back again. So some people find useful the notion that the north is very cold. No one want to live there. That's why everything is living north and goes back to south. And then inside of the magnet, magnetic field points from south to north again. Well, our Earth, our planet, is a huge magnet. That is why we can use the compass to navigate, right? We know that. And the easiest magnetic field, of course, is a uniform magnetic field. It's magnetic field where if we place a compass, we would observe exactly the same effect on it at any location. Now, as I said, a wire generates magnetic field, and the magnetic field of a wire depends, of course, on the distance from the wire. We will be using this equation tomorrow. For now, just an analogy between electric field and magnetic field. For electric field strength, we used a charge and a distance squared. But if we have a long wire which generates magnetic field instead of a charge, of course, we use electric current. No electric current, it doesn't generate any field. And the magnetic field strength decreases with distance, just distance. Well, because it's not a point object, it's a very long object. And this is a new physical constant which represents a relationship between magnetic field strength using international system of units. So electric current has to be measured in amps, amperes, distance in meters, and in that case, the number for the magnetic field strength will be measured in so-called Teslas. Tesla, International System of Units for Magnetic Field Strength. And 1 Tesla is a very strong field. It's hard to generate it. So there's a smaller unit people use in physics, but we're not going to use it. Just if you ever read Gauss, you know it's a fraction of a Tesla. Now, this is how we can study magnetic field. This is a very strong magnet. So what can I do? I can take a compass and place it between the poles, and I see how the arrow points. And the direction of the magnetic field here outside relative to you is to the right, from north to south, that way. But as we said before, a wire with electric current starts acting like a magnet. And as we know, two magnets interact. They might repel or attract each other. So when a wire with electric current is placed in a magnet, it should experience a force. Should it? Yes? Well, it does. And what is the direction of this force? Up. Now one knows. All right, now I lost my direction. So, red electrode represents high voltage, which means electric current through this wire should travel like this, from plus to minus. So when I turn it on, electric current through this part of a wire will be traveling to the right. And I place it like this, to the right. Now represents toward you. What do we see? Force. So a magnetic field, the direction of electric current and the direction of the force are related. Of course, I can change the direction of electric current. And now we can see the force points in opposite direction. What else could I do? Well, I could change the direction of magnetic field, and that would again change the direction of a force. So there is a rule which relates the direction of a magnetic field, the direction of electric current in a wire, and the direction of a force acting from magnetic field on a wire. And that rule has a name. Right Cartesian reference frame, XYZ. Here, x-axis represents the direction of electric current, y-axis represents the direction of magnetic field, and z-axis represents the direction of a force. So this is one convenient device you can always carry with you if you ever need to relate the direction of electric current, magnetic field, and a force. But there's also a different way to represent XYZ axis using your hand. In that case, if you use your hand, the rule has a different name. It's now a right-hand rule. And in this rule, the index finger should represent the direction of electric current, or x-axis. Those three fingers should represent the direction of the magnetic field, and the thumb will represent the direction of force acting on a wire. That's it. How do we know it? Because of hundreds of years of experiments, this rule has never been broken. It always works. That's it. That's what physics comes from, experiments. Now, how do we measure the force acting on a wire? Well, we have to attach it to a force meter, dynamometer, spring scale, and measure force. And then we measure this force for different values of electric current, for different values of magnetic field, because we can change it by generating it in a wire, and also by changing the orientation between a wire and magnetic field. And after all those experiments, first two conclusions are, number one, sometimes even if electric current is not zero, even if magnetic field is not zero, there is no force. And that happens always when magnetic field and electric current parallel or anti-parallel to each other. When there is no angle, or angle is 180. In that case, there is no force. But if we start changing the orientation of a wire from parallel to more and more and more, to finally to perpendicular, turns out that gives the maximum possible value for the force acting on this wire from this magnetic field. We assume that we don't change the value of electric current. We don't change the strength of magnetic field. We only change the orientation. And when we measure the force, turns out it changes depending on the angle. And when a wire and field perpendicular to each other, force reaches maximum possible value, which is equal to this product. I represents current in amps. B represents magnetic field strength. What does L represent? This wire is 1.5 meters long. But when I place it here, only this portion of a wire is in the magnetic field. So what does L represent? Only this portion. Because other parts of a wire not being affected by magnetic field. So L represents only that portion of a wire which is affected by magnetic field. And this is actually how we can measure the strength of magnetic field if we use this backwards, because we can measure force, length, current, and this will give us the strength of magnetic field. Well, now, of course, we need to say something about the general situation. See something, say something. So when we have a uniform magnetic field, these arrows represent the magnetic field which is the same in magnitude and direction everywhere. Let's say we place a wire in this magnetic field at a certain angle. What we can do is to imagine that this wire is actually composed of many tiny wires, which are either parallel or perpendicular to the magnetic field. Actually, there's an easier representation. If we add all those tiny parts which are parallel to the magnetic field, we get a line like this. If we add together all those tiny parts which are perpendicular, we get this. But they all together represent the same original wire. That black wire should experience exactly the same force as original red wire. So how do we calculate the force acting on that black wire? Well, it has two parts. This part experiences no force. And the second part, this part, will experience the force equal to only this. Segment. Only that part of a wire which is perpendicular to magnetic field is responsible for the existence of the force. What do we do now? Well, of course, we do some geometry. This is the actual length of the wire. This is the angle between the magnetic field and the wire. So, if we use trigonometry, this is how we can relate the hypotenuse and the side, which is opposite to the angle. We can use it here. And of course, we get a general expression for the magnitude of the force acting on a wire with electric current from magnetic field, assuming everything is constant. Magnetic field is constant and uniform. Electric current is constant. Yeah. And these pictures represent the right-hand rule. How do we use these pictures if the angle is not 90? Well, we know that only that part of a wire which is perpendicular to magnetic field matters. So we imagine that electric current has a component perpendicular to magnetic field, and that's what we use for the index finger. Magnetic field lines point, well, here to the right. So in this example, force acting from magnetic field on the wire will be directed into the screen away from you, and we have used a symbol for that direction. So remember, we have 6 standard directions: up, down, left, right, into the screen, out of the screen. And for each direction, we have a special symbol. This is for up, this is for down, this is for right, this is for left, and this is, or this is for into the screen or away from you, from your eyes. And what is the symbol for the opposite direction? Out of the screen or out of the page toward you. This symbol represents the force acting on this wire in that direction, perpendicular to the screen toward you. How do we find it? Well, the right-hand rule. So I don't point my index finger along a wire. I only point it along a component of the current perpendicular to magnetic field. These fingers always point in the direction of magnetic field, that magnetic field. So, and I look at the thumb, and I see the direction of a force out. Now, common mistakes is using a claw. If you know that a vector can be bent, you don't do that. Every direction in this rule is a vector. They have to be straight at 90 degrees to each other. Now, another common problem is trying to not break your wrist when you do this. So if it's a screen, it's a screen. But if you use your own picture, instead of rotating your hand, you can rotate your picture. The motion is relative. Now, we know how to calculate the strength of force. Now we know how to find the direction. So the natural question is on the screen. So here you have a symbol which represents electric current. And this symbol tells you electric current points away from you. So it's like this wire, but it's horizontal, points away from you, and electric current travels into the screen. And here we have magnetic field. Well, there is a magnet, and this line, this vector represents magnetic field line at the location of this wire. And you should choose the direction of a force acting on this wire. And I've got a couple of more things to show. So I'm going to use this. By now, you already have chosen your answer. So you don't need this screen anymore. So this is a model of our globe. It's a magnet. So if we walk around, we can measure magnetic field with a three-dimensional compass. And another important difference between the magnet, oh, see how strong it is. It attracts the globe. Important difference between the magnet and the electric charge. Magnet always has two poles. So, oops, attracts, repels. If I break it, oops, don't eat it, it's not chocolate, it's magnet. It still has two poles, attraction, repulsion. I can break it again and again, but I still cannot ever separate the poles. It's not like charges. This is a big magnet. How do I know it's a magnet? How do I know it's not just something made of iron? Well, attraction. If it would have been a magnet, I would have to observe repulsion. That's not the case. So this nail has no poles. Here, attraction. But if I see repulsion, that means it's a magnet, has two poles. And if I break it, how strong I am, it still has two poles. Attraction, repulsion. Oops. They're happy. Finally, something happening for them. So, let's see, that was question number 4. Still working. 8. What was 8? What was 8? There was no 8. Oh. Was 8 correct for 3? 1. Okay. 1 is electric current, magnetic field. 1 is correct. That's it. So now you know. One more question. Well, this question gives me time to prepare for calculations, which are very simple in this particular problem. But you should, again, use the right-hand rule. Now the angle is not 90 degrees, so it makes your reasoning a little bit harder. So, red arrow represents the velocity of those electrons which travel in the wire. What do we know about electrons? Negative. What is the definition of electric current? For the direction of electric current, we defined motion of fictional positive charges. So, if you remember that from the past, you answer this question correctly. Otherwise, you do it the opposite to correct. Because if electrons travel like shown, that means for the actual direction of electric current, according to the definition, we should use the direction of the motion of fictional positive charges. So that's supposed to be the direction of electric current. And only for that we can use the right hand. For electrons we can use left, but that's a couple of slides after. Now what do we do? Well, now we know we should only look at one component which is perpendicular to magnetic field, and that will point up. So electric current points up, and magnetic field points to the right, so the force will be into the screen. How do we calculate it? Well, we just have to plug in numbers. What do we know? Electric current is 2 amps. The length of that part of a wire is 2 meters. Magnetic field strength is given in Teslas. That's it. And the sine theory is on half, so 0.3 newtons. But if we know how to calculate force acting on a wire from magnetic field, now we know how to solve any problem about a force or many forces acting on a wire. Because that wire, this wire, might be just floating in the air. How could that happen? It could happen if magnetic force and force of gravity cancel each other out, so net force equals 0. So as soon as we said that word, force, we know what to do. What is the first action related to force problem? What is the very first action we have to do every time when we have to solve a problem related to force? Free body diagram. So the force may have a different nature. However, the approach is not different at all from the one we've used for all other forces. It starts from a free body diagram, always. And then whatever happens, happens. So read, please. Think, choose, enter. I'm going to use this time to drink my coffee. And to clean up this. I'm not going to need it anymore. All right. So what's your answer? Yes, I saw you moving. Five is correct. In both parts. First of all, there are no elves. Secondly, we know very well, because we studied it, that electric current in a wire is the result of many, many charged particles traveling together, which means the force we are observing on a wire is just a result of many, many electrons being acted, which means if we have only one electron, still should be force acting on it. And how would we calculate that force? Well, we would have to calculate the force acting on the whole wire and divide it by the number of electrons. That would be force acting on a single electron. So the idea is simple. We can measure a force acting on a wire. And then if we know that force on wire divided by the number of charges, that will give us the force acting on a single charge. That's it. And we can do that because we know that electric current equals total charge traveling through the wire times time. And total charge will be equal to the charge of a single electron times the number of electrons. And also, divided by time, sorry, Q over T. And also, we know that distance over time is speed. So, if we combine all these simple equations together, we get the result. If we have a single charge traveling through a magnetic field, it experiences the force. Well, not always. There is one exception. That exception is here. If velocity of a charge is parallel or anti-parallel to magnetic field, there will be no force. But if the velocity of a charge has a certain angle to the field, there will be force. Maximum force is reached if velocity of the charge is perpendicular to the field. And in between, it depends on the angle. How? Based on same function, the sine. But I don't usually use this equation if I need to analyze what's happening to the charge. I use this equation. This equation tells us that to calculate a force acting on a single charge, we have to multiply three numbers. The magnitude of that charge, the strength of the magnetic field, and the value of the component of the velocity perpendicular to the field. If there is no component perpendicular to field, that's zero, no force. Yes? You see, I haven't said a word about direction yet. I've been talking about magnitude only. So far, just about magnitude. Now, when we used the right-hand rule for a wire, we used the direction of the fictional positive charges. But of course, if we would use an actual positive charge, a proton, the direction of the force would be related with the direction of magnetic field and velocity by the same right-hand rule. Because when we make a transition from a force acting on a wire to a force acting on a charge, we think of positive charges. So for a force acting on a proton or any positive charge, we can always use right hand. For the electrons, what should we do? We should use left hand, opposite one. Or you could apply a right hand rule, but then in the end you would have to flip the direction of the force to the opposite. So you're absolutely right. Two different charges would experience different forces in the same magnetic field, even if they travel with the same velocity. Positive charge experience a force according to right-hand rule, and a negative charge will experience force according to the left-hand rule. See, RHR, what does it mean? What do you think? Right-hand rule for positive charges. Because it's been derived from a force acting on fictional positive charges called electric current. Well, question, this is a positive charge, let's say it's a proton. It travels to the left. This is a snapshot, a photograph, because if a force is acting on a charge, of course, acceleration is not going to be equal to 0, and that means velocity will be changing. That will be our next part of it talk. But at this instant, if we take a snapshot, velocity points to the left, magnetic field points diagonally. First, you have to choose what hand you want to use. That depends on the charge. If it's a positive charge, right? If it's a negative charge, left. That's it. And of course, you don't use the actual velocity, only that component which is perpendicular to the magnetic field, right? So, perpendicular to magnetic field, this. This requires dealing with vectors. So, this is an important part of geometrical reasoning. Now, we use the right-hand rule. The index finger should point diagonally this way, magnetic field this way. So, the thumb shows the force acting on this charge. But if you want to, if you can make something like this, well, smaller or larger, and use it. And students have done it before, so some find it useful if you have a prop like that. You just have to mark them, which is which. So, that's a lot of new information which has to be internalized, which means memorized, because definitions don't require understanding. They just require memorizing and then being applied accordingly. Please spend 30 more seconds or a minute to answer this question. Now it's an electron. Magnetic field points out of the screen. These symbols represent direction out of the screen toward you. So that's how magnetic field points. We can assume a magnet behind the screen with the North Pole facing us. So magnetic field, and an electron travels down. So first we have to choose what hand to use. Negative charge, left. Now, well, I always start from velocity. Velocity points down. Now, the hardest part is to make a right orientation. Well, I can use a fact that I'm free to move. So this is how I can do it. Velocity, field, force. That's it. Now, because a force is acting on this particle, acceleration is not 0, and velocity must change constantly. What does it mean? Well, let's just imagine several snapshots for a particle traveling in a magnetic field. So let's say we have a region with no magnetic field, and the particle is entering positive charge. Let's make it positive, it doesn't matter. It's easier to use the right hand. Entering magnetic field. Here, magnetic field starts acting on it. Well, magnetic field, let's direct it into the screen. So this is a standard representation of magnetic field directed away from you into the screen. So it's region. So the particle travels straight ahead because nothing is acting on it. Here, first time when magnetic field starts acting on this particle, of course, first we have to draw a force. So we have to apply the right-hand rule. So velocity, magnetic field, force. This is the instantaneous picture. Now, we know that according to Newton's second law, F equals ma. Now, of course, in this situation, there is only one force acting on this particle, magnetic force. So acceleration has exactly the same direction as the force has. And we know that if we wait a fraction of a second, the new velocity will be equal to initial velocity plus acceleration times time. Time might be a fraction of a second. So how do I find the new direction of velocity? I have to know how to add vectors. This plus this times tiny number. So something like this plus this. That's supposed to be a new direction of velocity. Where? Well, the particle doesn't stop. It travels. So in a fraction of a second, this particle will be, well, here, somewhere farther into the field. But it will have a new velocity directed slightly up. But if velocity changes the direction, according to right-hand rule, force must change the direction, because the force must remain perpendicular to velocity. So velocity now changes the direction. Force also must change the direction. And this will be the new direction of the force. And now we know what to do. We just have to repeat this reasoning again and again. So particle keeps traveling. It will be here. New velocity, new force, keeps traveling. New velocity, new force. So if we draw the trajectory which connects all those locations, turns out it's a circle, well, a part of a circle, an arc of a circle. So, a conclusion. Particles which enter magnetic field at 90 degrees to it, in magnetic field, travel in circles. Circular motion. What do we know about circular motion? From PY105, week 4. Everything we need. So all we have to do now is just apply our knowledge. So the strategy, of course, is very well known. Because it's about force, we have to start from a free body diagram. There is velocity, force, acceleration. We show it. We have to write the Newton's second law. Normally, no other force is acting on a charge in the magnetic field if it travels in a circle. So only one force, magnetic force. We know how to calculate the magnitude of that force. It actually has a name, Lorenz's force. And the force acting on a wire is Ampere's force. So, and then we have to solve it. For a circular motion, we also know that acceleration has a specific relationship with speed and radius. So we can calculate everything. Here, well, of course, we need only a snapshot, a photograph, one location of a charge in magnetic field. In my picture, magnetic field points. How does it point? And we have 6 standard directions, up or down, left or right, into the screen or out of the screen. And you have to be able to read those symbols. So how does magnetic field point? Anybody? Out of the screen. These symbols represent out. It's like a bow arrow. You're looking at the tip. It shoots at you. You have to duck. If you see feathers, that represents direction away from you into the screen. This is out of the screen. So we only need one location. This is a charge, and let's say this is the velocity, instantaneous velocity, and magnetic field points out of the screen. So positive charge, I make it positive for simplicity. Velocity, field, instantaneous force points to the right. Will the force always be directed to the right? What do you think? No. It's a circular motion, so the trajectory is an actual circle. What does every circle have? Every circle has it. What is it? Radius, center. So we have to show that the center, that's the radius. And the centripetal acceleration always points toward the center. And if a particle keeps traveling at a new location, centripetal acceleration will be directed differently, or force. That's what we know. But again, we need only one location. Now, F equals ma, Newton's second law. Now, because direction constantly changes, we don't really want to care about it, so we just relate magnitudes. How do we calculate the magnitude of the Lorenz's force? This is how. How do I know the angle is 90 degrees? I have eyes. My eyes tell me that when one vector points up and second out of the screen, the angle between these two directions is 90 degrees. So, and that should be equal to m times, this is not just a generic general acceleration, that's a centripetal. We have to know how to calculate the magnitude. So please tell me, anybody. V squared over r, exactly. This is our initial equation. We can derive from this equation anything. Well, first we can cancel one speed, because v on the left, v squared on the right. And what's left? Q b equals mv r. And well, we can solve it for speed, for example. Yeah, that's going to be q r b over m. Also, for the future, we can solve it for v squared. That's going to be equal to q v b r over m. Why would I need v squared anytime? Well, kinetic energy, for example. So anyway, what else can we do? This equation relates 5 different variables. Well, this equation here is solved for the radius, which means if we know any 4, we can calculate any 5th. Also, we can analyze these equations to see how change in the magnetic field, for example, affects something else, the radius or something else. So this is an example. What do we need to do if we need to decrease the radius, keeping everything else but magnetic field same? Well, we look at the equation. Magnetic field is in the denominator. If everything else remains the same, changing magnetic field, well, increasing magnetic field decreases the radius. Now, let's take a look at the beam. See? This is a standard vacuum tube. It has a filament, and when it's heated up, it emits electrons, and then electric field picks it up, accelerates electrons, and we can see how this beam is affected by a magnet. All we have to do is just have a magnet and bring it close, and we can see that let's say this is the North Pole, red one. So if I get in closer and closer, this beam deflects down, which means the force should point down. Now, if we know the direction of magnetic field and direction of the force and velocity, we can figure out what kind of a charge is that, positive or negative. So we can try, okay, let's try using the right hand. Magnetic field points out of the North Pole. Velocity points to the right. But if those charges would have been positive, force would deflect them up. That's not the case, so what does it mean? Those are electrons. Of course, those are electrons. And do you think you're looking at electrons? You cannot see electrons, no one can. But those electrons just travel through a specially prepared paper, and it's a luminescent paper. So it's not electrons with green, it's a paper. Now we can make them move in a circle. All we have to do is just apply a uniform magnetic field, and for that we use specifically prepared coils. This is a high voltage, and that is a high voltage power supply. So wherever we use a power supply like that, we have to be very, very careful. Now what I want to do? I want to do this. Oops. Again, those are not electrons, of course. There's a gas which emits green light when electrons collide with atoms. So if I change magnetic field strength, I can change the radius of this circle. Stronger, weaker field. When there is no field, they travel straight ahead. So if there is a relationship between the strength of the field, the radius, and other variables, we can use a setup like that to actually calculate something related to the properties of those particles, like mass or charge. And that's going to be your lab tomorrow and on Thursday. Maybe I need light. Let be light. So, quickly, a period. Well, we just have solved the Newton's law for the velocity. Velocity will be equal to r times q times b over m. Now we just have to apply a definition of one period. A period, it's time for a particle to make one whole revolution, which means it travels exactly one circumference or exactly one period. That's it. So if we solve it for the period, first of all, radius canceled. So it's going to be equal to 2 pi m Now, interesting conclusion. If we have different particles, but if they have the same mass to charge ratio, well, two different particles with the same ratio in the same magnetic field, they will travel with the same period. And we're not saying with the same speed, no, we're saying the same period, because they might travel faster and slower, having different radius, but the period will be the same. Now, this is what I just said. Next, kinetic energy. Well, kinetic energy equals mv squared over 2, not r. Well, we can just do it again. M over 2, and we have to square the speed, the radius, charge, magnetic field over mass. So r squared, q squared, b squared over 2m. It's a more complicated relationship, but basically, anytime when we need to calculate kinetic energy, we can just do this. Now, we know something very important about kinetic energy. It only changes when net work is done. So the next natural question is, if we have a charge traveling in magnetic field, circulating in magnetic field, can you say something about the work done by magnetic field on that charge? In this situation, we have a proton which circulates in a uniform magnetic field. The work done by the magnetic field on the proton is take the last glance on the slide. I'm going to switch to WebAssign. Choose your answer, pick it up. Switching. Checking. That's a question number 9. Lots of questions today. 7, 8, 9. Oh, we already start having distribution. So, once more possible answers, please. Pick yours and enter it. Now, We always have several approaches in physics to answer the same question. The right and wrong answers, all of them presented. For example, here, actually, here, the particle, the charge, might be located along the circular path. Where? Well, circular-ish. Anywhere, here, 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 here. Does our calculation of kinetic energy depend on the location? No. So what variables might affect kinetic energy? Radius, charge, magnetic field, mass. If it's same particle with the same magnetic field, making circle with a fixed radius, does kinetic energy change? What do you think? Yes. Yes. There are only three possible answers. Yes, no, I don't know. No more. I don't want to know. I don't care. So what do you choose? Does kinetic energy change? No, the variables are constants. There is no change in the kinetic energy. So it does not change. There is no work. Kinetic energy does not change. There is no work. And we actually had a very similar situation discussed before. For example, a conical pendulum. Yeah. We give it a spin, and it rotates. The only reason it eventually will stop is because of the friction. But if there would be no friction acting on it, it would spin forever with the same speed. And another way to think about it, about direction, because no matter where, here, 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 if we draw two arrows, velocity and force, the angle between those two directions is 90 degrees. And when we need to calculate work, we'll have to multiply by cosine 90. Cosine of 90 is 0. So several approaches. Same fact, magnetic field does not do any work, which means it does not change kinetic energy, which means it does not change speed. Velocity does change, because velocity also has a direction, but speed remains constant. For example, in this situation, we see three particles. They enter magnetic field, travel with constant speed, and then they leave magnetic field. And we have some information provided about some particles, and we have to use that information to figure out everything we can. And the first question is, what do you think is the direction of magnetic field? So this region represents part of a space with magnetic field. That magnetic field might point up, down, left, right, out of the screen, into the screen. And we should choose. Bless you. So please tell me, anybody, what do you think is the direction of magnetic field in that region? How does it point? Does it point to the left? No, there is no such answer provided. but it has to point somewhere. And to figure it out, you have to choose a particle. You need to know, is it a positive or negative particle? You have to use your hand, not your mind. You're thinking, that's wrong. You have to use your hand. Can we choose particle B? No, we don't know if it's positive or negative. But particle A is positive, and particle C is positive. And particle C has an initially horizontal velocity. Now, you have to draw a vector which represents the force acting on particle C when it enters the magnetic field. So it was traveling, like in my experiment, it was traveling to the right and enters magnetic field and immediately starts being deflected. So here and now, what is the direction of a force acting on this particle from this magnetic field? And again, we have 6 standard choices, up or down, left or right, into the screen, out of the screen. So what do you think? Bless you. Now you have to say something. What is the direction of a force acting on this particle here? Force. You have to use, which hand do you have to use? The right, it's positive. So now use it. How do you point the index finger? Why? The index finger has to point in the direction of velocity. The blue arrow represents velocity. So how does the index finger point? To the left. Now, we use this rule to figure out direction of magnetic field, which means now we have to say something very specific about the direction of the force. And that's what I was asking you. That's what I was asking you. What is the direction of a force acting on this particle? Here, because it changes in time, but right here, it must point in a certain direction. How? No. It can't be into the screen, because into the screen or out of the screen has to be magnetic field, and these 3 directions must be perpendicular to each other. So neither velocity nor force cannot be directed into the screen or out of the screen anymore. Down. Why? You applying right-hand rule to a situation when you have to apply right-hand rule. You have to use something other than the right hand to state the direction of a force first, and only then you can start applying right-hand rule. So the answer is correct, yes, but the reasoning is still kind of not clear enough, at least. Why is force directed straight down? What is the reason for that? Anybody? Let's talk. What do you think? Because it's a circle. Well, it's not complete circle, but if we had the whole magnetic field surrounding the whole trajectory, that would have been the circle. Your circle must be better than mine. Anyway, something like that. What does every circle have? And a circle cannot have acceleration. Particle can. A circle is a geometrical shape. That's it. It has center. It begins from the special point, center. Center. How do I know this is the center? Well, I know how circle is shaped. So this is the radius of this circle. This is the radius of that circle. And I also know that acceleration in this situation is not just general acceleration. It's centripetal acceleration and must point toward the center. And I also know if I multiply that acceleration times mass, that will give me a force. That is why force must point down, because the center of the circle is down, below that location. But now, finally, I can use the right-hand rule, because I now know 2 directions out of 3. So, velocity, force, and these fingers now show that magnetic field should be directed out of the screen. So we use the right-hand rule differently. Once we used it to find the force, now we use it to actually use the force and find the direction of magnetic field. It always can be done if we know or assume that they're all perpendicular to each other, which is almost always the case. So magnetic field points out. We can add that information. This is how we show it. That symbol points out. Now we know what to do. We can again follow the same strategy. We did something. We figured out the direction of magnetic field. That action has been done. It's behind us. Now we ask the question, what can we do now? We can draw a free body diagram. We finish that action, and we ask question, what can we do now? Well, maybe write an equation. We did it. Then we ask, what question do we ask? What can we do now? Okay, we can simplify that equation, solve it algebraically. What can we do now? We can plug the numbers and use a calculator. What can we do now? Be happy. That's how it works. I will solve this tomorrow, but for now, let's stop. So you know now all the strategy. Thank you. Yeah.
So we don't have labs today?
No. No labs today. Labs tomorrow and Thursday. If I remember correctly, you should have sent me an email a couple of days before to remind me about it.
You told me to come to lecture, and I'll take it after.